So talking more in general about polynomial functions, a quadratic function is a polynomial, but in general, a polynomial function of degree n is a function that matches this form. And what is it about that? It says where n is a non-negative integer, so all of these powers that we're raising x to has to be an integer. We're not raising it to 3/2 or anything like that. Okay. And it also says it has to be non-negative. We're not raising it to -1 or anything like that. Raising to positive whole numbers. Okay. And then all of these a values are the coefficients. All right. And so we call, just for notation's sake, we call a sub n x n. That's the leading term. All right. It's the one that has the highest degree. You know, and this is the coefficient that goes along with it, the highest power. All right, that's the leading term. That's going to tell us a lot about the shape of our graph. Okay, a sub n is the leading coefficient. Okay, that's also going to be important. And a sub 0 is the constant term. That will be important at various times as well. Okay, different types of polynomials. All right, when we have degree 0, then we just call that, anybody want to take a guess? If the highest power on the variable is 0, what kind of function would that leave us with? Okay, a line, or we'd say a constant function. Okay, a horizontal line, it's constant. We don't have any x's, we just got, you know, x to the 0, which is 1. It's a constant function. If we have degree 1, we call that what? That's more of a linear function. Okay, linear function when we have x to the 1. Second degree we just talked about is what? Quadratic, very good. Third degree is cubic. Fourth degree, I think we call it quartic. I might have made that up though. And the fifth degree is something, I don't know. Okay, but they keep on going. Okay, these are the different polynomials that we'll be talking about. No, not so much. Yeah, no. We'll look at all of them in general. Okay, some properties of polynomial functions. The domain of a polynomial function is all real numbers. We can plug anything into it. The graph of a polynomial function is a continuous curve. Okay, we don't have any jumps or gaps or breaks. And it is a smooth curve. It does not look like this. It's smooth curves. Okay, so. Oh yeah, we'll look at all kinds of ways. It's just not those angled lines. Okay? There's lots of information in this section, in this chapter. Little clues. And all of math to me is like a puzzle. All right? The puzzle is going to be to look at one of these big polynomials and be able to graph it. So we'll be introducing little clues, and you need to try to kind of understand what they're telling us about the function. Okay, so the first one talks about the shape of the polynomial. It says a function of the form f of x equals a times x to the n is called a power function of degree n. Okay, where a is a non-zero real number, n is a positive integer. A power function is the simplest nth degree polynomial function. We don't have anything else following this. Okay, just that highest powered term. So it says power functions of even degrees are symmetric with respect to the y-axis. All right. So when I think about 7x squared, 10x to the 4th, 20,000x to the 6th, okay, all of those things have an even degree, right? Yes. and they basically look like this, some variation on it. They're going to be symmetric with respect to the y-axis. All right, if that's all that we have. Everybody understanding what I'm saying? Okay, so we already got an idea about what that kind of function looks like. If the degree is odd, like x cubed, we already have an idea about what x cubed looks like, then it's going to be symmetric with respect to the origin. Okay, this blue one is x cubed, the pink one is x to the 5th, the green one is x to the 7th. Okay, all of those are odd degrees, and they basically have the same shape. All right, you got it? Okay, good. All right, so keep that in mind, because that goes along with what we're talking about here next, which is the end behavior. Okay, end behavior for the graph of y equals f of x equals a times x to the n and the leading term test, or the behavior of the graph of this polynomial. Okay, if n is even and a is positive, then the end behavior of the graph is like this. Okay, now in between, the graph might do all kinds of stuff, but the end behavior is going to be like that. Okay, what does that have to do with what we just talked about? We just said if we have an even power, what does it look like? Very good. It's symmetric across the y-axis. That was a very simple polynomial. It only had that one term. But when we start to add different terms, then we get all this other behavior in the middle. But the end behavior is still the same. Okay? All right, so just paying attention to that first term, whether or not the power is even, and in this case, a is greater than 0, so we know that it's going to open which way? Up, okay? Then we get this kind of behavior. If a is less than 0, but we're still even, then we get down on the left and down on the right. Okay, in the middle, whatever else goes on, but when it gets to the end part, we're going to be down on the left, down on the right. Okay. If the function is odd and a is greater than 0, we already have in our mind, the basic x cubed thing. It looks like that, right? So it's going to be down on the left, but what on the right? Up. Okay, in the middle, it'll do some different things, but this is our end behavior. Down on the left, up on the right. If a is less than 0, then this whole thing rotates, it flips about the x-axis, so we're going to get what? That's right. Okay, in the middle, other things will be going on, but that's what the end behavior looks like. Okay, so when you get ready to graph your function, at least you know what the end behavior should be. Okay. For example, okay, determine the end behavior of the graph of each function. So in this first one, when I look at that function, I notice that the leading term has what kind of power? 6, which is even, and the leading coefficient is positive. It's 1, positive 1. So that means it's going to be what? To the left, up, and to the right, up. Okay? Up on the left, up on the right, if you want to use some words. Okay, up on the left, up on the right. All right? But this next one, f of x equals negative x cubed minus 2x squared plus 11x plus 12, when I look at the leading term, what kind of power do I have? Odd power. And so that makes me think of, again, this. But then my leading coefficient is negative. So on the left, I'm going to do what? Up, and on the right, down. Okay, and whatever else goes on in the middle. Okay, questions about what that tells us? Okay, it's a little tiny clue, but really, really, really important. All right. Can y'all tell I'm starting to get excited? No, y'all can't tell. Okay. All right. Something else that we'll talk about, zeros of a function, and we'll be using some of these terms interchangeably, so you need to be aware of that. It says C is a zero of a function if f of c equals 0. C is a zero of a function if when I plug C into the function, I get out 0. Okay, that's what we mean when we say it is a zero of a function. You might have known that, but there it is for the record. Okay, if f is a polynomial function and c is a real number, then the following statements are equivalent. Okay, again, we'll use these things kind of interchangeably. Okay, first of all, c is a zero of f means the same thing as c is a solution or root of the equation f of x equals 0. Okay, those things basically tell us the same thing. Okay, c is an x-intercept of the graph of f. That is, the point c0 is on the graph of f. And a polynomial function of degree n has at most, this is a separate statement, but I went on and added that in here. Polynomial of function degree n has at most n real zeros. Okay, and I already showed you that when we looked back at our graphs of x squared, a long ways back apparently. Wow, we talked about a lot. What happened to those things? You remember I had all those graphs of what x squared could look like on a graph? No, y'all don't remember that. That was today. Okay. Remember, x squared is a second degree polynomial. And what I showed you is that most we would have how many zeros? 2. We'll never have 3. Okay. We could have at most 2. We saw where we would have 1 or possibly none. Okay. So the degree of the polynomial tells us how many solutions to look for. Okay. If I've got a 10th degree polynomial, it's possible that I can have 10 real zeros or 10 real solutions, but I can't have 11. It's going to be at most n. Okay, let's see. All right, looks like we're looking at end behavior again, and they ask us to find all of the real zeros of the given function. Okay, so what's our end behavior on this one? Okay. Is left going to be down? Okay, on the left we're going to be up because of the negative. Okay, and then on the right it's down. Okay, but how do I find the zeros? Well, of course, I'm going to set this thing equal to 0. And if I can, I will factor. Can I factor this? Okay, yes. When we have 4 terms, what factoring method do we use? Or at least try to use? Grouping. Okay? So I'm going to try to use grouping. I'm going to group the first 2 terms, group the second 2 terms. If I look at the first 2, I can factor out negative x squared. I'm left with, very good. Okay, and then over here I can factor out I'm left with x plus 2. That didn't work so well. Let's see. What else can we do? Well, I'm wondering if I don't have a typo here. I can't think of anything else that we've talked about already that's going to let us factor this. So I'll come back to this next time and find out if I made a typo or whatever. But certainly, if we can factor by grouping, then that's what we would do. Okay, so we'll review that a little more next time. Alrighty. Here is another rule that will be helpful to us. It says let A and B be two numbers with A less than B. If f is a polynomial function such that f of A and f of B have opposite signs, then there is at least one number C between A and B such that f of C equals 0. Does that make sense? No. Okay. Basically, we've got a graph. There's a value A, there's a value B. Okay, and on the graph, f of A, which might be right here, and let's say f of B, which is over here, they've got opposite signs. One is positive, one is negative. Okay, then if the graph could do all kinds of things, it might be a straight line or it might go up and down. But in order for me to go from negative to positive, I have to go through what? Which is, what's the value there? 0. Okay, so somehow if I know that one of these values gives me a positive and the other gives me a negative, then between them there has to be a value that gives me 0. And that's what we're looking for. We're looking for those values that give us 0. So for instance, it says use the intermediate value theorem to show that each polynomial p of x has a real 0 in the specified interval. I could show that if, when I look at p of 1 and p of 2, they have opposite signs. There has to be something between the two of them such that p of whatever that number is would be 0. So what's p of 1? 1 minus 1 is 0. Minus 2 minus 5 looks like negative 7. Yes? This is an interval. So an interval from 1 to 2. Okay? P of 2 is what? 16 minus 4 is 12. Minus 4 again is 8. Minus 5, I got 3. So P of 1 is negative 7. P of 2 is 3. In order to get from negative 7 to 3, I had to go through what? 0. Okay, so since P of 1 and P of 2 have opposite signs, and P of 2, yes. There exists a 0 in the interval from 1 to 2. Okay, there's a 0 in that interval. Okay, what do we mean by 0? We mean a value such that if we plug it into the function, it's going to give us 0. All right, questions about that? Okay, excellent. Okay, multiplicity of a 0. And maybe this will be our last little concept of the day. If C is a 0 of a polynomial function f of x, and the corresponding factor, x minus c, occurs exactly m times when f of x is factored completely, then C is called a 0 of multiplicity m. Okay, we've got, let's say we factored, we got x minus 5 to the 4th power. It has multiplicity 4. Okay, and so that tells us something about the graph. It says if m is odd, the graph of f crosses the x-axis at x equals c. It actually comes right on through. Okay, let's say we got C here. The graph is going to come through the point. Okay. Versus if m is even, it's going to touch it but not cross. So that looks like, okay, in both cases, we have a 0 at C, right? Does everybody see that? But when, did somebody say no? You don't see it? Oh, okay, all right. So, but when m is odd, it comes right through. Okay, versus if the multiplicity is even, then it's going to touch it, it's going to bounce back. So we're learning a lot about the behavior of our graph. Here in the example, it says find the zeros and give the multiplicity of each zero. Also indicate the behavior of the graph at each zero. Okay, and I've got a nice little table, it looks like. Okay, so first of all, what are our zeros? This is already factored for us. So what? What is it? Okay, -1 and 6. And also x equals -3. Okay, those are our zeros. Okay, because we take this function, it's already factored for it, set it equal to 0, set each of the factors equal to 0, and then we get x equals -3, x equals -1, and x equals 6. Okay? Multiplicity of -3 is what? So we'd say 2, which is even. And so what are we going to say? The graph touches at x equals 2, or rather x equals -3. Okay, it touches at x equals -3 but does not cross. All right. At x equals -1, what's going to happen? The multiplicity is not 0, 1, which is odd, and so it's going to what? Cross at x equals -1. Okay? And then at x equals 6, that multiplicity was also odd, and it's going to cross at x equals 6. Okay?